All right, so we are going to get into the lovely world of Devicenet. And just like we've been kind of doing the last few weeks, we're going to watch the lovely video first, and then we're going to go through my lovely little PowerPoint. So that lovely video I'm talking about is the one that is on D2L. What is Devicenet? 5 R's. You guys should be used to these people by now. Obviously, I really like the videos. All right, so this is something we haven't actually talked about. We've talked about terminating resistors a lot. All right. This is telling us 121 ohm, 1%, 0.25 watt or larger is what it just said. All right. What is 121 ohm?
Like the measurable amount of distance.
All right. That is what the resistance should be if you were taking a multimeter and measuring. All right. What is the 1%? Okay, good, close enough. Tolerance is what we call it. All right. So that means that 121 ohm should be within 1% of that. So if you were to take 121 times 0.001, right? I think I should use my hand, but I'm sorry, 0.01. We should get 1.2 ohms. All right. So that means that we could go down to 119.8 to 122.8. That would be the acceptable range for a terminating resistor. All right. Now, 1%. They're out there, they're not too hard to find. All right, 5% is probably like the industry standard. All right, so like if you just grab like a little bag of resistors, right? You know, one of those ones that we've used in class before, probably gonna be a 5% resistor. All right. So this is saying it needs to be within 1%. I'm curious how close it actually needs to be within 1%. All right, but anyway, and then 25 watt. What does that mean?
It's like how much wattage you can handle.
Excellent. Close enough. Good. Good. It's 0.25. I think it's a 25 watts. 0.25 watts. All right. So this is a quarter watt resistor. All right. So that means, again, like if you're sending 1 volt through it, you could send 0.25 volt amps through it and get quarter of a watt. All right. But if we're doing like 5 volt signaling, our amperage has to be a lot lower. All right, now this is just going over the data line, so this shouldn't have much current going through it anyway. All right, but it is something that is definitely important to think about. All right, most of these like little itty bitty resistors, and I should bring this up. Is it 6 that I picked? 6. All right. Anyway, so this one of these little resistors, that's either an eighth watt or a quarter watt. I don't know which one this specifically is, and it's very hard to tell. But there are color bands on there. Okay, this isn't really electricity class, but those color bands tell you what value this resistor actually is. For those who don't remember that. All right. All right. So this one looks to me like it's brown, black, orange. So brown is 1, black is 0, orange is, let's see, big boys race R 3, so this would be a 1,000 ohm resistor if I were to measure this. And then this has I think it's a gold band. I can't really tell, but you have gold, silver, and I think there's another color for your tolerance. All right, I'm gonna guess this is the 5%. But anyway, that is like a quick resistor thing. Yeah. Obviously, they're showing you this like nice little picture of a device that's at the end of the cable. So this isn't just like a little quarter watt resistor that you could grab out of your parts bin and like twist the wires. All right, but those resistors are always going to be important. So I just want to quick talk about the whole 1% thing. We haven't talked about that at all this semester. Here we are at the very end, but it is an important fact to think about that. For percentage of it, and is it actually within an acceptable range? So could you use a 5% resistor? Yes, you just want to like multimeter first to make sure it's actually within the range that it's desired to be. All right, so yeah, one of those things just to think about. Obviously, the higher the percentage, the lower the manufacturing cost because they don't have to check each one as much to make sure it's within the acceptable range. So yeah, little give and take going on there. They go from we've got this picture of Devicenet way from the top. They go from one that doesn't work to one that does. That's a huge difference, and obviously why just with CAN bus. We probably had the same issue going on, right? We had crazy signals that we couldn't decode, and as soon as we put that resistor on, boom. It was like, okay, now we have nice resistor, nice information, because we don't have that feedback, that reflection coming back down the line. It's bouncing back and forth. All right, so going to be very important in the long run. All right, so as the video talked about, quick history here. We have the ODVA, which is the Open Device Net Vendor Association. All right, this was in the long run created by Alan Bradley, right? Because they're the one that created this, and then they said, hey, we're going to create this as an open resource so anybody can use it. And hey, you want to use it, right? All right. All right. So anyway, Alan Bradley is like the main PLC brand. So they showed other possible ones. I think they said Omron and Schneider were on there. I've never seen anything but Alan Bradley that uses this. Now I will also be the first to say that I am not the most widely known, of all this information. But everything I've seen, Alan Bradley is the one that uses Devicenet. All right. And this was been around like the 1990s when Alan Bradley developed this. All right, so this is a low-level device-oriented network, which means it's designed to interconnect lower-level devices such as sensors and actuators with the high-level devices like controllers, like PLCs, and those type of things. All right, this is based on CAN. Holy crap, we just talked about CAN. Isn't that crazy? So, we have a variable multi-byte format of the CAN message frame. It's well suited to this task, as more information can be communicated per message than with a bit-type system. So that's why I like the CAN bus stuff. All right, and yeah, we can go ahead and continue that. All right, so this supports up to 64 nodes. All right, now this is definitely a variation from CAN bus, right? Because CAN bus was an 11-bit ID. All right, and that was like what, 2000 or something? I think it was 2000. Let's see, 11. Yeah, 2048. All right, if this is only 64. That would be 2 to the 6. All right, so we've almost like halved the ID. Now again, 64 for like one PLC to handle is probably plenty. All right, especially if you're trying to keep latency down. If you want to be able to get as much information out of all devices as possible without all sorts of things, it's definitely good to have lower latency and things like that. So restricting the number of devices probably a good idea. All right. The video talked about removing devices without power. All right, and I guess we're going to take a little detour here, and we're going to go to the wonderful world of these actual Devicenet devices. Trying to get this in focus. There we go. So here we have a Devicenet, and this would be inputs and outputs. So we've got, I'm assuming blue is inputs and green is outputs, but it could vary. It could go either way. And then we got a little door here so we can actually see all of our screw terminals and things like that. And then down here, we've got our connector. And this is one of those connectors that they talked about in the video. All right. Let's see. Can I pull this out? Making a huge mess. So we've got this lovely little connector here, and that will just, flip it over, just plug right in, bada bing, bada boom. All right. And what is kind of different about this connector is if we notice right here, we've got a spot for wire there and a spot for wire there. So we can actually put a wire in and a wire out on this connector. Like, it was designed almost purely for that purpose as far as I'm concerned. So we've got screw terminals on the bottom to tighten wires, and we've got screw terminals on the top to tighten wires. So it makes our life really easy when it's like, okay, we want to daisy chain things. It's just, okay, come in from your trunk line, for this wire, and then this one would go out to the next device. And you can just keep doing that. You can keep daisy chaining up to what, 20 feet, I think is what they were saying, right? And they keep talking about this, that it can be done without removing power or screwing up the network, right? The video talked about that, I think, a few times. But anyway, because you can just plug this in, and it plugs in, the trunk line in the next device, and when you unplug this, it only removes this one device from the network. The one that's connected on this daisy chain here is still connected. So we're not breaking the network. We're not disconnecting the terminating resistor. Everything else is perfectly fine. It's just the one device that we took out of the loop. So if you had to replace this one device, you could come here, unplug it, unscrew everything, screw what you need to back on, plug it back in, and be good to go again. All right. Now, we've also, as I said, talked about node devices. How do you think we set the ID of this? It's going to be simpler than you think. You open this little flap here, and if we were looking there, we go. you can see that there are two little dials with numbers. So you literally just take a screwdriver and go, this is device 16. You go click, click to 6 and click, click to 0, and you're done. All right, and this does also tell you MSD and LSD. What does that stand for? Yep, most and least. All right, so which one's the left, which one's the right? Really what it comes down to. So very easy. This one, bigger version. All right, and this one is actually expandable. You can see that there's a port here on the side, so you could actually keep stacking more and more I/O on this. All right, there's our Devicenet in, and then we have our device ID, node ID select right there. So you would just push the little buttons on this one. Grab my wire. So you would just, boop. You guys can't see. There you go. So you just push the little button and it just increments it by 1. All right. Now, to me, the interesting thing here is both of these will actually let you go over 60. But that's just because, available technology, right? It's like, why get a custom-made piece that goes from 0 to 6 when I can just put a 0 to 10 9 one in and not have to, get all this extra stuff and just tell you, don't set it over 6. All right. So a little bit of game going on there. I'm a little too hot for this microphone. All right. Anyway, so those are our actual devices that we're talking about. Now, in the video, they did talk about like specific sensors or flow control and things like that. And yes, you could do those. These are just discrete I/O add-ons. So instead of having to run individual cables from 20 I/O that are 100 feet away, right, we just run a device net to this. We put this right by all the I/O. We don't have to run a bunch of cable. So a little bit simpler in the long run. All right. Also, the video talked about the kilobaud rate, the baud rate. So we're doing 125K, 250, or 500. Although a specific installation may allow all 3 of these, it doesn't have to actually support all 3. All right, that's kind of annoying. So take that as you will. But depending on the distance you're traveling, which we've talked about this many times throughout the semester, right? The farther you're traveling, the lower the baud rate. Now this standard only allows 3 baud rates. All right, it's not like serial where you can be like, I want to go down to 100 baud. Just all the devices are talking at 100 baud. No, that doesn't work in this case. You also notice that like serial, we talked about 9,600 bits per second. This is saying a minimum of 125,000. So we are worlds faster than serial here in this instance. All right, so a little, again, give and take going on there. Now, for topology here, all right, we've got a few different options. All right, so across the top, we have our trunk line. All right, again, that's going to be our main connection. All right, and we talked about how it needs to be 120 ohms for our terminating resistors at the end. So we can see those. There we go. Got our terminating resistors there and there. That would be our trunk line, and we've got different drops. So drop lines can be up to 20 feet in length. All right. However, you have to make sure you don't go over your max drop line budget. All right. So if our max drop line budget was say 100 feet or whatever, and each of these was 20 feet, you'd say 20 and 20 is 40 and 20 is 60 and 20 is 80 and 20 is 100 and 20 is 120, right? Like, yeah, we just exceeded our max budget there for that. So you do have to think about that. And as the video showed, if you had 5 feet to here, and then 5 feet, 5 feet, 10 feet, or actually, just go with 5 feet again, you have 5 feet plus 5, 10, 15. So you got 20 feet of drop line there, even though it's like, well, the max distance is only 10. But yes, but because you got all 3, you got to take all 3 into account. So they're kind of acting like each like their own little drop line in that instance. Same thing with over here. This was, 5, 10, 15, 20, going on. So we do have to think about that. All right. And drop line length and trunk line length is going to be determined based on the speed. Remember, the different speeds, different cables. We may actually find that little nice little table they had again. So, types of cables. We have thick, we have flat, we have thin. All right. So lots of different options. Let's show you 5 different options. All right. So we have thicker flat cable is used for long distance runs and is stronger and more resilient than the thin cable. Probably makes sense overall. You need a thicker diameter cable for longer runs, so we have less voltage drop, so we can have better signaling capacity. All right. That one just makes sense. You have less resistance, you have less voltage drop. All right. And then again, the rigidity there also should make sense. So thick cable is used for, when length is important. Our overall diameter is about half an inch, 0.48 inches. Our signal pair wire size is 18 gauge. That is going to be twisted pair. And then our power pair wire is 15 gauge. Now, which one's bigger? Which one's a larger diameter? 15 gauge or 18 gauge? This is a lovely question. It's a trick question. Which one's the larger diameter? 15 gauge or 18 gauge? You're saying 15? You agree? And got one person knows their stuff, and everyone else is agreeing. You are correct. That's a good system. Look at the wire cutters. All right. So yes, the 15 gauge is larger. So they're saying, okay, we're gonna have a larger diameter for the power because we have to have like actual current over this, not just worrying about voltage drop. So a little bit of give and take going on there. My notes say that this gives you an 8 amp capacity for the power. And we're also going to have a braid copper shield of some sort. The thin cable, this is going to be used for drop lines or short trip lines. Overall diameter is only 1/4 of an inch. That's half the size. We have 24 gauge wire for the signal and 22 gauge wire for the power. That's only 3 amps of capacity on the power. So you can see that's a big difference, 8 amps and 3 amps. All right. And then the flat cable is rated for 600 volts, 8 amp rating. This is not twisting, but it's highly flexible. So a little bit of give and take going on there. And that's here we can see some of the differences. All right. So you've got your thick wire, you got your thin wire, and then you got your flat wire. So notice they're all 64 nodes. That doesn't change at all. All right. Our cumulative drop length is the consistent for everyone. So it's 512 feet for the first, 256 for the second, 128 for the third. Our drop length does not change. They're all 20 feet. But what does change is the trunk distance. So at the fastest speed, right, our thick and our thin, according to this, has the same amount of distance. Although if you notice the thin wire here, all the trunk distances are exactly the same. That's kind of interesting to make like that. Well, some question will go on there, but that's what the spec is rated for. But if you go to the flat wire versus stick, you'll notice that we go from 75 to 100, 200 to 250, or 420 to 500 meters. So there's definitely a difference there. So a little bit of give and take. Now, one of the big benefits of that flat wire is making connections. All right. I don't know if you guys have seen them, but there are connectors out there. None of these on the screen are what I'm talking about. But there are connectors out there where you can basically just pierce through wire and not actually have to like cut it to put a slice in. So like you could run a 200 meter trunk line, and then wherever you need it, you just snap this thing over the wire and it allows you to slice off of it. So you don't have to cut it and whatnot. So it really allows you to put a drop anywhere you want. But that does not exist for twisted cable wire because you don't know which wire is in what position and whatnot. So the flat wire gives you a big benefit in that aspect. So a little bit of give and take going on there. All right. So there are two main types. We've got T-taps and multiple port taps. And then we've got open and seal. All right. So a T-tap would be this, and I'm actually going to overall, no, that's not a T-tap. That's just like a, let's see, no, not a T-tap. This would be a T-tap though. All right. So at the top and the bottom are our two T-taps. Oh, another little T-tap right here. It's the same as the bottom though. All right. Trunk line goes in, trunk line comes out. We're going to drop coming off the bottom. All right. So overall, T-taps make sense. Multi-port would be this one. I don't have a multi-port. Let me open. All right. The open versus the closed. It's all talking about this is watertight or dirt tight or whatever you want to go with. And as you noticed, the one I showed you earlier, there ain't nothing protecting this cabling. All right. Those wires are basically an open contact, just like you guys have probably signed up throughout the semester. You screw the terminal down, you're done. All right. Nothing about those is protected. All right. Where this one, the top here, this T-type, if you notice, it's got, they're trying to show you, there's threads here and a little nut that you screw over it. So it's actually a little, I think a little O-ring on there too. That makes a nice, watertight seal. All right, so depending on your environment and what you care about, you may like the ease of use of this open type where it's like, oh yeah, I can just cut a wire, put them in, screw terminals down, and I'm done. Right? It's really easy to replace something or whatnot. However, he may like I like the sealed aspect because we're in a very moist environment here because we've got water boiling or whatever the case. We've got lots of steam going on. So you don't want those contacts corroded. So you got to take a little give and take going on there. What's more important for you? Ease of changing or ease of protecting your stuff? So a little bit of give and take going on. All right, so power requirements. All right, so this is interesting. Like, okay, we're gonna have power on the network, right? But like that's one of the big selling points. You have power on the network. You don't have to run individual power supplies. It's all wonderful. It's great. So but there's a lot of things in conflict. All right. So let's see here. So we have a dedicated power supply for the Devicenet network. Right? You're gonna have that. This could be both thick and thin type. You're only gonna use one type of cable per section network. Yeah, okay. So, is this on my next slide? No. Oh, yeah. Okay. Anyway, so if we had a 200-meter network, all right, and our current current for the sum of nodes 1 through 5 is 0.65 amps, all right, using cable, I guess it's 13A, 13, all right, yeah. What cable type are we going to use? Are we going to use thick or we're going to use thin? So you can see there's two different types. All right, which one are we going to use? So just a reminder, we're having a total of 0.65 amps and a network length of 200 meters. Which type are we going to use? You're going thick? Why are you going thick?
Thin at 20 meters as a maximum current of 5.
We're at 0.65 amps. 0.65. So we're nowhere near 5 amps. We're under an amp. So could we use thin? Two parts to this. You got the one part. You got the amp part. What was the other part I talked about? Distance. 200 meters. Which one? Thick or thin? Crazy guys. Which one can go 200 meters? Thin, right? Thin can only go out to 100 meters. So instantly, just ignoring carrying all together, you're like, well, yeah, we can't use thin cable. That only goes to 100 meters. So if you want to go 200 meters, we have to use thick in this case. All right. All right, my next one. All right. So now, I think actually, yeah, okay, that was supposed to be my little picture for you guys. Although I'm now realizing that I think this probably gives it away for you, but Okay, so let's go to the next one. So here we have it. We got a single supply where actually our power is in the middle here. All right. So we've got 90 meters to the left, we've got 120 meters to the right. So we have between those like 210 meters. Fix that. We've got, again, 0.65 amps. That's wrong. You can ignore this. We've got 0.65. Section 1 is 1.05 amps over the length of 90 meters. So if we were to add up all that, you'd get 1.05 amps. And the other one is 1.88. And 8 amps. So, my question for you is, what can our cable be? Thick or thin? For which one or both? We're saying thick for both. Why?
So the one to the left has a length of 90 meters, but the maximum current that can be done through thin is only 0.78, we only have 1.5.
Okay, I like that logic. What about the other side?
The thin cable can't go to
Excellent. All right, if we go to 150 meters on the thick, we get 2 amps. So we're all in the good. We're all in the clear there, I should say. All right. So when you're picking your cable, there are things that you need to think about. The power budget is going to be important. All right. So max voltage output is about allowed to be 5 volts on each line. Thick cable trunk line current is 8 amps. Thin is 3. All right. Max drop line 0.75 to 3 amps, depending. And then our voltage range at each node is 11 to 25 volts. So a lot going on there. Let's see. My notes also do say when you're doing these calculations, be conservative. Right? It's like, oh, that device is going to use half an amp. It's like, well, just plan it for an amp, or 3/4 of an amp or something. Right? Don't go, oh, the minimum for that device is going to be half an amp, but the max could be up to 0.75. We're going to use the point, we're going to use a half. Now, you don't want to do that. You always want to be on the conservative side. Let's always assume worst case scenario. At most operating, that's going to be this amount of voltage. As long as you do that, you're going to overbuild the system, right? Because okay, well, the lowest, if you have 3 nodes, they're all low as 0.5 and they're all high as 0.75. The likelihood of them all using 0.75 at the same instant, not very likely. But if you assume it, you're going to always have a big enough thing. Your power supply will be big enough, the cabling will be thick enough. Worst case. The other benefit of oversizing is what? So, I'm going to build a bridge from point A to point B that can handle one person, one car at a time. All right. Well, actually, it was a 1-lane bridge, right? Go down to Funkstown, take a right light, go over a little 1-lane bridge right by the fire there. All right. They built that. It's a beautiful bridge. It's great. It's got 1 lane. What problems does that come to nowadays? Traffic, right? It's 1 lane. You only need 1 car at a time, going one direction at a time. So I've seen probably 20 or 30 cars backed up there at times because it's like, oh, never. And depending on people, it's like, I'm gonna let 1 car go, and it's gonna be your turn. And that's like, I go 4 or 5 cars at a time, right? Get the traffic going, less starting and stop. But they didn't future-proof when they built that bridge. Or the future-proofing they thought they did was cars or vehicles, whatever's going over is only this wide, so we can do 2 wide. Now normal cars are double the width. Oh, now we can't do 2 cars wide. All right. Maybe they thought it was supposed to be a footbridge, bike bridge, horse bridge, something like that. And paved it in cars. Like, okay. I don't know if that's actually true. It might have been designed as a 1-car bridge, but the 1-lane bridge. But anyway, future-proofing is always good. It's like, well, right now we only have these devices. So in 4 years, your boss is like, hey, let's add some more blah, blah, blah. Now I have to pay you to run more cable because you didn't oversize it. So it's costing them, A, twice as much in cabling because they had the original in and now this thicker wire in. And B, it's costing them twice as much hourly wages. So I'm always a big fan of future-proofing as much as possible. And depending on how hard something you're doing is, run 2 wires instead of 1. It's like, well, I can run 1 wire, I can run 2. It's going to be the same hourly cost. So it's going to cost us an extra $50 or $50 in cable. Lost, I go do it. Because if one of that cable breaks, and now I have to pay you again and the wire, so now we're double dipping. You might as well just run a second cable right off the bat, future-proof yourself, and not necessarily for Devicenet. Right? It's like, oh, we ran this cable, it's got 4 conductors and a shield in it, and then your boss is like, hey, we run a serial connection. It's like, oh, I got an extra cable here, we can do it over that. Right? Just make your life simple. It's really what it comes down to. So I'm a big fan of future-proofing, not only in the industrial world, but my house as well. It's like, okay, we're running a power line from smoke detectors. I'm like, well, let's run that conduit so we can also run our Ethernet cable up to the roof as I'm doing that. So I was like, well, we're also putting insulation, below insulation. I didn't have to walk through 6 or 8 inch, 10, whatever insulation I had to roof. I didn't feel like having to deal with that. So it's like, we're going to run Ethernet cable right away. Do I have plans to use Ethernet? No. But it's there for when I want it. So I can just put ends on both sides, plug it in whenever I need to, and I can put a server or Wi-Fi access point or a camera or whatever up in my attic. Obviously, don't put a camera in the attic, that'd be worthless. But you guys get my point. Think about future-proofing when you can. Your boss may be like, no, we're not spending the money. But when you can future-proof, not only with pre-running things, but also have equipment on hand. You're like, if this switch goes down, we're boned until we can get a new switch. All right. So if you can, buy an extra switch, just have it ready to go. All right. HTC does that with their networking. They have at least one backup of every network device, I think. All right. So it's like, oh, we're putting a new building in. They don't have to go waiting for the budget to come so they can order the equipment and then put it in 8 months later. They go, okay, we've got 4 of these on hand. We'll put those in temporarily. We'll buy the new stuff. We can either replace it or keep those now stacked. All right. So it saves you a lot of time in the long run by doing that. Makes your life a little bit simpler. So future proofing is great. All right, and then the last thing here is fragmentation. All right. So a single frame can only be 8 bytes. That's 64 bits, right? So what if I had this lovely device, and this one is only 15 or 16 and 16, so that would be fine. What if I kept stacking more of these on here, and I needed more, or I'm sending analog information back? How do we handle that? All right, and the key here is fragmentation. So we can take information and we can say, okay, here's one frame, here's another frame. We're just splitting up that into multiple different sections to allow us to transmit it. All right. So as you can see here, the first byte is always 0, 0. All right. So here's our data packet up at the top, or 0, 0, 12, 34, 50, whatever. All right. And then if we had to fragment this, we would say, okay, instead of starting with 0, 0, we're going to start, well, sorry, this is 1. Here's another byte. Here's another byte. And then here's the last fragment. So here's what we're sending. So it's like, okay, 0, 0, say, hey, this is packet number 0. 12 is going to be, man, we're using some of this for our ID, right? Because we're doing 6 bits. So that would be, actually, that'd be 2 bytes. Yeah, it'd be less than 2 bytes. So this would be our ID, and then we've got our packet information, and then we've got our flows or whatever the case is. And then we go to the next one. That's 41. And then 42. And it's like, okay, this is the last one between 80 and FF, so 83. And here's your last 2 bytes of information. All right, so we can take it, we can split it up into multiple different smaller bytes, so that way we can send all of it at once. And as long as your protocol knows how to deal with that splitting up and bringing it back together, obviously you could go to the moon with this. Right? And this is how basically all protocols are working. When you're sitting, like, when you're downloading a file off the internet, they're not streaming you all 1 gigabit of those bits at a time. No, they are breaking it into a whole bunch of smaller packets and sending it to you when your computer's downloading it. And the crazy thing here is, when like internet networking, when they're streaming it to you, right? You've got your Amazon server here, and you've got your house here, and you're going from here to here to here to here to there to there to there to there to there. All right. When they're streaming it to you, the packets might be going like packet 1 may take this route, packet 2 may take that route, packet 3 may actually do this. All right. All the packets aren't necessarily going the same way. So your computer is getting all of these in, and it's going, man, how it comes back together. All right. And that's where those first bytes are very important, how they're very specifically ordered. So that way it knows, okay, here's the first byte of information. Oh, there's 41, that's second. Oh, I got 83 next, that's not the next one. Oh, here's 42. Oh. So it can now rebuild that information it's sending. So having that specific order is going to be very important. Not so much here because you are sending it one after the other across the same trunk line. So there's only really one path for you to take, but it's still going to be very important for you. So. All right, and that is all I've got for Devicenet.